Hello everyone, Mr. Fawcett here, and we are back with part 2 of our optimization problems lesson. During the first part of this lesson, we talked about what an optimization problem is. We did go through one example. Hopefully you did that hands-on activity where you attempted to build your box that had the most volume before you went through and tried to look at the calculus techniques for it. Moving on, we are going to just go through a couple of different examples where we are trying to optimize something. And remember, optimizing doesn't always mean we're finding the maximum value. It could also mean we're finding the minimum value of something. So we're going to start with problem number 1, and we'll just get through as many of these as we can without making the video too long. So it says a solid is formed by joining two hemispheres to the ends of a right cylinder. The total volume of the new solid is 12 cubic centimeters. We need to find the radius of the cylinder and solids that produces the minimum surface area. Okay, it may be easy, or it may be most efficient to start with a diagram here. And with the diagram, that may show us, what variables we're using, etc. Okay, so here's a very, very rough sketch of what this may look like. And we are told what the volume of this solid is. We are told that the volume is equal to 12 cubic centimeters. So we're going to come up with an equation for the volume, but this is a different type of solid. It's going to be made up of different volume equations, right? We're going to have the volume of these hemispheres, which is based on the radius. And these hemispheres are congruent, so the radii should be the same. And then we have the volume of the cylinder as well. Volume of the cylinder is going to be not only based on the radius, but also based on the height of the cylinder. So and you could think about this, if we have two hemispheres, well, that's going to be like having one sphere. So volume of a sphere is equal to 4/3 pi r cubed. And the volume of a cylinder is equal to pi r squared times the height. Generally, if you're being given one of these problems on the AP Calculus exam, they are going to give you the volume equation because they don't want you to not be able to do the problem because you forget a geometric formula. They're testing you on the calculus, so they're not testing you on the memorization of certain formulas. If it's a very basic formula, like the area of a triangle or the area of a square or something, or the area of a prism, like a rectangular prism, they may not give it to you. But if it's one that's not used as frequently, they're more likely to give it to you. So again, if we're trying to find the volume of this entire figure, well, we would just add these volumes together, right? So we get the volume of the whole figure is equal to 4/3 pi r cubed plus pi r squared times h. So this is one equation that we're working with. And you know what? Let me actually move this. Wish I had more space to do this problem, but it's okay. Let me move this down here below. Because we also have another equation we need to work with, right? It says that we need to find the minimum surface area given a volume of 12 cubic centimeters. So now we need to know the surface area of a sphere as well as the surface area of a cylinder. Well, let's start to break those down. Surface area of a sphere is equal to 4 pi r squared. Again, we're looking at a sphere because two hemispheres would make a sphere. Now, we also need the surface area of a cylinder, but we don't need to include the bases, right? We just need to include, so if I redraw this cylinder here, I do not need to include the bases because they're covered up by the hemispheres. So they're not going to be included in the surface area. So the surface area is just the outside surface there, not including the bases, and that is going to be 2 pi r times h. Again, we're not going to go too into depth as to why these formulas are what they are. That's more of a geometry concept. We're just going to now look to utilize these formulas, which means that our total surface area would just be the sum. So surface area is going to be equal to 4 pi r squared plus 2 pi r times h. Okay, so we've got a couple of equations. Now, it says find the radius of the cylinder and solids that produces the minimum surface area. So we're going to be looking to solve for the radius. You'll notice that our surface area equation has two different variables, though, that could change. It has the radius and the height, and both of those could be different based on what our solid over here ends up looking like. So we have to rewrite the surface area equation in terms of just the radius. Now, we can use our volume equation to do that, right? Because we're not quite done with our volume equation. We were told that the total volume is equal to 12 cubic centimeters. So let's substitute 12 in there. And let's get h by itself. If we can get h by itself, we can then make a substitution into this equation and replace that h. First thing we're going to do is subtract 4/3 pi r cubed from both sides. And then I'm just going to divide by pi r squared. So I'm going to end up getting 12 minus 4/3 pi r cubed all over pi r squared. That is equal to h. Looks a little messy, but we can use it. And we are going to substitute that in our h in our surface area formula. So let's rewrite that surface area equation. Surface area is equal to 4 pi r squared plus 2 pi r times 12 minus 4/3 pi r cubed all over pi r squared. Now this is going to be where they test our algebra skills, because I'd really like to simplify this before I take the derivative, right? I don't want to have to do the product and the quotient rule here mixed up with a bunch of power rules. So let's try to simplify what's in purple and make it a little bit easier on us when we take the derivative of the surface area. I am going to clear some of this out just to give us some more space. Of course, you all can always just pull out an extra sheet of paper. I'm going to move this purple quantity. Oops, let's make sure I get all of it. Without getting any of the black. That's not going to do it. Let's try that one more time. There we go. Okay, so let's start to simplify. I'm actually going to break apart my quotient here. So I get 12 over pi r squared minus 4/3 pi r cubed over pi r squared. Of course, a couple different ways you could do this. I'm going to then distribute my 2 pi r to both terms. So I get plus 24 pi r all over pi r squared minus 8/3 pi squared r to the fourth all over pi r squared. And now I can do some simplifying. Not sure why I changed colors there. Surface area is equal to 4 pi r squared plus 24 over r minus, and I can bring this 3 down to my denominator. So I'm going to get 8 pi r squared all over 3. I'm even going to do one more thing just to make sure I have all my r's in my numerator. So I'm just going to write that as 24 times r to the negative first minus 8/3 pi r squared. Okay, I am now ready to take the derivative of my surface area function. Let's give ourselves some even more space. So I get the derivative of the surface area, or surface area prime, is equal to, and again, I'm taking the derivative with respect to my radius. So I get 8 pi r minus 24 over r squared. I kind of did 2 steps in one there, but you can go back and just double check that power rule that I did, and then rewriting the r with a positive exponent, minus 16/3 pi r. Now again, this is going to be a calculator problem, so once you have your derivative equation, that can go straight into your y equals, and you can just look for where the zeros are. I guess I should clarify, this derivative is undefined when r is equal to 0, right? Because then we would have an r, oops, did not mean to do that. Because then I would have an r, or is doing it again. There we go. Let's try one more time. Because then I would have a 0 in my denominator, but if we had a radius of 0, we wouldn't have a solid at all, right? This solid would not exist. So we're just looking to see where the surface area derivative is equal to 0. And again, you can just substitute that function right into your y equals and look for the zeros. All right, and we see that this only occurs at one r value, and that's going to be r is approximately equal to 1.420. That's going to be the same value whether you round it or truncate it. We do want to make sure that this is a minimum, but because this is a calculator problem, we don't have to do a whole number line. We can just look at the graph. If you look at your graph, you get something that looks like this. So clearly, and again, this is my surface area prime graph, so the derivative is going from negative to positive at that r value, which means that that is a relative minimum of our original function. The only thing we need to do to finish off this problem is make sure we include our units, so we know that this radius is in centimeters. And that's all we need to do, right? We don't have to find the actual minimum surface area, we just have to find the radius that will produce a minimum surface area. A lot of moving parts in these problems. They are kind of a culmination of several different concepts, really, Algebra 1, Geometry, Algebra 2, all the way up through things we've learned in calculus. So they're not meant to be finished in just a couple minutes. They will take some higher levels of critical thinking than some of the other problems we've done in this course, but they're also exciting because we get to put multiple different moving pieces together. Let's see if we can squeeze one more in. I know we're already at about 15 minutes, but I would like to do one more example. Okay, and we can work with number 2. So it says a rectangular page is to contain 24 square inches of print. The print is not going to include the margins. The margins at the top and bottom of the page are to be 1.5 inches. The margins on the left and right side are to be 1 inches, or 1 inch. What should the dimensions of the page be so that the least amount of paper is used? And again, it may not be very clear, where to even start. But anytime there's going to be a figure, like a geometric figure involved, I like to start with a sketch. That can kind of help us determine what variables we need to use and maybe what type of equations to set up. So it does say we have a rectangular page. So I'm just going to draw a rectangle. And it says there's going to be 24 square inches of print. So the print is going to fall somewhere inside. It does say the margins at the top and bottom are to be 1.5 inches. I'm going to leave off units for now. We will make sure to have those in our final answer. And the margins, oops, that was a poor 5. And the margins on the left and the right side are going to be 1 inch. And again, not drawn to scale. It's okay as long as we have it labeled correctly. So we need to find the dimensions of the page, and that's the entire page, so that the least amount of paper is used. Okay. Well, let's come up with dimensions for let's do dimensions for the blue rectangle first. I'm just going to call that x, the length, and we'll call the width y. Because we don't know they're the same, it is a rectangle. Now if I come up with dimensions for the whole page, well, it's going to be x plus those 2 margins. So it's going to be x plus 3, 1.5 twice. If I come up with a dimension for the entire width, I'm going to get y plus 2. Okay, again, a lot going on here. Let's see if there's anything else I can look for in the original scenario. Maybe that'll help us come up with some equations. So it says a rectangular page is to contain 24 square inches of print. So that's the blue page we're talking about. So I just need to find the area of that blue rectangle. Well, that's going to be x times y is equal to 24. Now, the other equation we're looking at is the area of the black rectangle, right? The entire page, because they want to find the dimensions of the whole page so that the least amount of paper is used. So my other equation for the big black rectangle is going to be x plus 3 times that quantity times the quantity y plus 2 is equal to area. Right? I don't know what that area is. We are going to try to minimize that though. Right? We want to use the least amount of paper. Okay, so you'll notice in the equation that we're trying to minimize, we have 2 variables. Well, I don't want 2 variables, right? I just want 1. So can I rewrite that black equation in terms of just x or y? And it's your choice. I'm just going to rewrite it in terms of x. And I'm going to use this blue equation to do so, right? If I just solve for x, I'm going to get x. Sorry, I want to solve for y because I want to rewrite in terms of x. So I'm going to get y is equal to 24 divided by x. I can take this quantity right here and substitute in for my y. So let's do that, and then we will worry about taking the derivative. I'm going to get x plus 3, that quantity, times the quantity 24 over x plus 2 is equal to a. Now, you could multiply everything out and then take the derivative. You could also use the product rule to take the derivative. It's really up to you. I am going to choose to multiply everything out. I think that may be easier when taking the derivative. So if I distribute here, I'm going to get 24 plus 2x. Distribute the 3 to both of those terms. That's going to give me 72 over x plus 6 is equal to a. Let me rewrite this with my x, my numerator, and let me simplify. So I'm going to get 30 plus 2x plus 72 times x to the power of negative 1 is equal to a. And this should be a pretty simple derivative to take. I'm going to put my a prime on the left-hand side. So a prime is equal to derivative of 30 is 0, derivative of 2x is 2, minus 72 times x to the power of negative 2, so which gives me a prime is equal to 2 minus 72 over x squared. Now, you'll notice that this looks like one we could probably solve by hand, right? If I'm trying to find the minimum value for area, well, I need to look from where my derivative goes from negative to positive. And I need to look for the critical points. Two possible things to look at. One is where the derivative is undefined. Well, this derivative is undefined at x equals 0. However, I can't have 0 for a length, right? If I say that x is equal to 0, well, I can't have 0 for a length. So that's not going to be in the domain of what my possible values could be. So even though the derivative is undefined at x equals 0, that's not going to be a possible solution. So I'm just going to need to figure out where the derivative is equal to 0. Let me put this up here. Actually, we can probably just solve it all right here. So I get 0 is equal to 2 minus 72 over x squared. That's going to give me 72 over x squared is equal to 2. That's going to give me 72 is equal to 2x squared. If I come over here, that's going to give me 36 is equal to x squared. And that's going to give me x is equal to plus or minus 6. So those are the two values where my derivative is equal to 0. Because this may be a non-calculator problem, we are going to have to check to see if our values are maximums or minimums by hand. Of course, we can immediately eliminate negative 6. Our page is not going to have dimensions of negative 6 inches. But let's go ahead and make sure that positive 6 is a relative minimum for my original function. So let's do a prime of 5. It's going to give me 2 minus 72 over 25, which is going to give me a negative value, right? Because 72 divided by 25 is almost 3. It's certainly more than 2. So that's going to give me a negative. And let's do a prime of 7, which gives me 2 minus 72 over 49. Well, 72 over 49 is less than 2, so that's going to give me a positive value. Again, you don't have to come up with the exact value here. You just need to show that the derivative is going from negative to positive. Well, okay. So when x equals 6, that is going to give me a minimum value for my large sheet of paper. And the only thing left to do is find the dimensions. It does say to find the dimensions of the whole page, which is the black sheet, the black rectangle. So my width, start with my length, because that was in terms of x. my length is equal to x plus 3, which is equal to 6 plus 3, which is equal to 9 inches. Okay, we know my length is 9 inches. Now to find my width, well, that was in terms of y, but I had a relationship between x and y. I actually just erased it, but we'll put it back over here. Right, I knew that the area of the blue page was 24. So I have 24 is equal to x times y. If x is equal to 6, I get 24 is equal to 6y, which gives me y is equal to 4. So my width is equal to y plus 2, which is equal to 4 plus 2, which is equal to 6 inches. So my width is 6, my length is 9 in terms of inches, and we are good to go. In these problems, it is important to make sure you answer the question that's being asked, right? So if you had just stopped with x is equal to 6, well, you've done 90% of the work correctly, but you're not going to get full credit, right? Because you haven't actually gone and found those specific dimensions. So just make sure you reread the problem one more time at the end. Make sure that you've answered what they're asking for, and then you can be confident that you're ready to move on. I think we are going to stop here. This video is pushing about half an hour. Again, these types of problems take a while. Just be careful, be tedious, be organized, and that'll help make sure that you're keeping track of all the important moving parts. As always, enjoy the rest of your day, and I will look forward to seeing you next time.